Okay, I guess we can start. Welcome to today's session of the Newton 1665 seminars. This week we're going to have a couple of sessions on less beaten tracks, and today we're going to talk about superdeterminism. And I think Alessandro would like to say some introductory words before we start. So please, Alessandro.
Okay, so just because this is an unusual problem in high energy physics, so maybe a brief introduction is useful. So one possible unusual question is what is the gadget that makes random numbers in quantum mechanics? So can quantum mechanics be some sort of statistical approximation to a deterministic theory? The usual answer is don't even try because of Bernoulli inequalities, but superdeterminism maybe is a way out, as we will hear today. And then tomorrow, Toft will present a possible idea along these lines. And next week, Gorard will talk about the Wolfram model. Okay, so let's start.
Okay, so Sabine, please share your screen and you can start. It's okay. The first speaker is Sabine Hossenfelder. Yep, please go ahead.
Okay. Well, first of all, welcome everybody. As Alessandro just said, this will be a talk about the foundations of quantum mechanics, and I think I want to start by saying that I've always been perplexed about the foundations of quantum mechanics, not because of the mathematics, but because of the way that the research area is organized. You have on the one side, you have lots of great experiments going on. And then on the other side, you have people talking about the interpretation of the mathematics. And in the middle between the two, there's a big gap. So this is where I would expect there to be a phenomenology of the mathematics of the quantum foundations. And there is basically nothing, not in the way that we have it in particle physics, where we have theory and experiment, and then in the middle between them, we have phenomenology. So what I'm talking about today is my attempt to fill in something into this gap where there should be the phenomenology. So it would be a little bit unfair to say that there's absolutely no phenomenology. There are the models with spontaneous collapse that I think reasonably can be said to be phenomenology. And I think this is not entirely unrelated to what I'll be talking about. So this approach falls into a type of theory that has become known as superdeterminism. And so I want to start with saying that so this is a talk about the foundations of quantum mechanics, but not about the interpretations of quantum mechanics. And if there's one message that I want to get across, it's that superdeterministic models are not interpretations of quantum mechanics. They're different theories from which you can derive quantum mechanics. So they're more fundamental, and in certain circumstances, they also make different predictions. And I wrote a paper about this recently together with Tim, who will be talking after me. So I want to first give you an idea of why I'm interested in this question. Quantum mechanics is a very successful theory, and that's great, of course, but fundamentally it just cannot be how nature works. And that's not because it is unintuitive or ugly, but because it is axiomatically inconsistent. And I want to spend a few words on this because I find that for the most part, the typical education that students get in physics kind of glosses over this problem. So in quantum mechanics, we have two equations that play the role of a dynamical law. This is the Schrödinger equation and the measurement update, which is also sometimes called the collapse of the wave function. And it's the combination of these two dynamical laws that leads to the measurement problem. So the measurement problem in brief is that quantum mechanics is not an ensemble theory. It's supposed to be a theory that, yes, it also holds for ensembles of particles, but it is also a theory for single particles. Now, what quantum mechanics tells you in certain circumstances, except for very special cases, is that you end up with a state that is with a certain probability in a certain measurement outcome. It does not tell you, well, the particle is measured in this particular state. It says it is in the state with a certain probability. And that's fine if you're speaking about an ensemble, but it's not fine if you're speaking about a single particle. A particle that's 50% measured is just not a thing. You know, it doesn't make any sense. And this is why we need this update of the wave function, because if you have the Schrödinger equation together with Born's rule, then you get this probabilistic prediction. But then once you measure the particle, you know that it is with 100% probability in a particular state. And the only way to accommodate this in your theory is to update the wave function so that now you're with 100% probability in this particular state. And this is just necessary to correctly describe what we observe. So this is the measurement problem, you know, that this assumption fundamentally makes no sense, as I will explain in a second. Let me just point out here that decoherence does not solve the problem, because the only thing that decoherence does is basically to convert quantum probability into a classical probability, but it does not make the probabilistic prediction itself go away. So in more detail, where does this problem come from? Well, the measurement process in quantum mechanics is not linear. If you have a state, say a photon or something, and you put it through a beam splitter, so now you have a superposition of the photon going into two different directions, then the outcome of measuring this state is not the same as the superposition of the outcomes for every single particle. So if you have a particle going left, it will go into the detector with into the left detector with probability 1. If you have a particle going right, it will go into the right detector with a probability 1. But if you have a particle that's in a superposition of left and right, it will either go in the left detector or in the right detector. It will not do both. So this is clearly a process which is not linear. And this means that it is incompatible with the Schrödinger equation. It just cannot be derived from it. But if you think that quantum mechanics is a fundamental theory that describes elementary particles, and you know that the detector is made up of elementary particles, then the measurement postulate should be, strictly speaking, unnecessary. The behavior of macroscopic objects in general, not only detectors, but in general, should be derivable from the rest. But this is not the case. And now you could say, well, maybe it's just really complicated and no one has been able to do it so far. But because the one equation is linear and the other one is not, we know that it isn't possible. So this is clearly an inconsistency if you think that quantum mechanics is a fundamental theory. The other logically possible option is to just give up on reductionism and say, well, the detector just does something that you cannot derive from the underlying theory. But I don't know how to make any sense of this formally on paper in some equations. So I do not think that this makes a lot of sense. So I'm afraid I'm a reductionist all the way down. The measurement problem has been known for a long time, of course, but it has remained unsolved. So there are the Copenhagen approaches and the neo-Copenhagen interpretations like cubism. They bring back the problem by just renaming it, you know, instead of talking about detectors, they may be talking about knowledge that is held by agents and so on. It's the same thing. You're bringing in concepts that are actually macroscopic that should in principle be derivable from the underlying theory. So you still have this inconsistency. Many worlds, there seem to be a lot of people who think that many worlds solves the measurement postulate. But you just bring it back in because you have to, in the many worlds, you have to tell, so if you want to make a calculation with the theory, you have to make a statement about relative to what you make the measurement. So you do not make your measurement with a detector that is smeared out over all possible branches. You only calculate the probability relative to the detector in your branch. And just formally, that's exactly the same as the measurement postulate. There's actually an easier way to see why many worlds does not solve the measurement problem. Many worlds is basically the same as the normal quantum theory, Copenhagen, that we have learned, except for the measurement postulate. And then it has a fancy interpretation on top of it. But if you just look at the mathematics, if many worlds was able to solve the measurement problem, it would mean that you can derive the measurement postulate from the Schrödinger equation in many worlds. But this would just mean that you can derive the measurement postulate from the Schrödinger equation, period. So the many worlds interpretation really has nothing to do with that. Yeah, and then there are models with a spontaneous collapse that I already mentioned in the beginning, and they do solve the problem in the sense that they tell you the state actually does go into a detector eigenstate by making little collapses along the way, basically. But this only works after you tell your dynamical law what state the wave function is supposed to collapse into. So you actually have to put this into the equation already, which is a little bit awkward because it doesn't seem to be quite local. Yeah, and speaking of locality, then there are pilot wave theories, and they kind of solve the problem, but they have an explicitly non-local ontology. And also, you know, I suspect that they actually have the same problem about having to specify what state to collapse into, but I have an ongoing argument with pilot wave fans about this, so I don't want to get into this. Okay, so what is the conclusion to draw from this? Well, I think for me, this just means that quantum mechanics is not a fundamental theory. It's an emergent theory, and the measurement postulate is an effective description for a complicated process in an underlying theory, which we have not yet discovered. This underlying theory is deterministic, but it has to be nonlinear, as we've seen previously, because otherwise you can't get the measurement process out of it. And it is what goes under the name of a hidden variables theory. This idea is also supported by the obvious similarity between the classical Liouville equation and the von Neumann Dirac equation. Now, of course, you can say, well, that's obvious, right? So clearly, if you have a process that is not deterministic, the first thing you would try is to come up with an underlying theory that's actually deterministic and try to derive it, right? So why hasn't anyone looked at this before? Well, of course, people have looked at it. It was pretty much the first thing that they looked at after the discovery of quantum mechanics. But as we have learned, notably from Bell's theorem, is that any theory that is deterministic local and solves the measurement problem must violate a condition known as statistical independence. And so here's the key condition of statistical independence. Lambda are the hidden variables that make the measurement outcome determined and no longer stochastic. And A and B are the measurement settings. So this equation tells you that the hidden variables are not independent on the detector settings. So violating statistical independence means essentially that the time evolution of the prepared state depends on the detector settings. And that's what's called superdeterminism. So superdeterministic theories have a bad reputation. And I now briefly want to tell you why and why I think that these criticisms are not justified. Yeah, before I do that, I have to briefly define exactly what I mean by superdeterminism, because not everyone means the same thing. So superdeterministic theory is a hidden variables theory, as I already said, that solves the measurement problem, and it reproduces quantum mechanics on the average. So it's a psi-epistemic theory in the sense that the wave function itself does not correspond to an element of reality. So it's like I could, I could take an average of the faces of everybody in this meeting or something, and I would get out a face, but the face itself would not correspond to anyone who's actually in the meeting. And so the wave function basically plays the same role in this kind of theory. It's deterministic. Interestingly enough, not everybody who works in superdeterminism also assumes that the theory is deterministic. I think if it makes no sense if it's not deterministic, because then why bother? And it is local in the sense that it does not have any spooky action at a distance. So any kind of interaction is supposed to travel locally and not jump through space. And then it follows from this that the theory must violate statistical independence if it's supposed to be in agreement with observation and be nonlinear, because otherwise it could not solve the measurement problem. Needless to say, it follows that it reproduces quantum mechanics, and that sounds kind of silly, but I point this out because it has happened to me quite frequently that people come back and say, yeah, but what about the so-and-so inequality and the blah, blah, blah bound and all that kind of stuff. And I'm like, well, yeah, if the theory reproduces quantum mechanics on the average, then it's also going to reproduce all these bounds. So, of course, you want to know how it actually reproduces quantum mechanics on the average. But once you have that, all the rest will be fine. Okay, so the literature is full of misconceptions about what the consequences are that I briefly want to go through. The major misconception is that this is just unscientific because superdeterministic theories are necessarily void of explanatory power. So that basically they say, well, you can't explain anything with this. But this doesn't make any sense because superdeterminism gives rise to quantum mechanics. So in the suitable limit, it just makes the same predictions. Now you can say, of course, well, if it makes the same predictions with more assumptions, then that's just useless. So why bother? But of course, you don't know how many assumptions you actually need until you've looked at your theory. So if it makes the same prediction with fewer assumptions, it has more explanatory power. And if it requires more assumptions, then it should give rise to more predictions. So whether or not it does that, you can only find out by writing down the complete theory and looking at it. Just by saying that the theory is superdeterministic, you just don't know if it explains more or less than quantum mechanics. So it just doesn't follow. You just have not enough information to even make that statement. Okay, so the second misconception is that it would make science impossible. If we would allow calling correlations between the prepared state and the detector an explanation, then science just wouldn't work. Okay, so the first mistake of this argument is fairly obvious, which is that by assuming that such correlations cannot explain anything, you've assumed what you want to show. You would actually have to tell me why this doesn't explain anything. But what's worse than this is the second mistake here is that just because statistical independence is a useful assumption for classical measurement, and no one denies that, it explains a lot, certainly, you cannot infer that it also holds for quantum experiment. That's just not an allowed inference. It's kind of, it makes about as much sense as saying, well, I have a lot of soccer balls or something, and look, I throw them in the water and they all float on top. I conclude from this that stones will also float on top of the water. Clearly, it doesn't make any sense. And also, I think this argument is just silly because science arguably works just fine, regardless of whether anyone talks about a superdeterminism. So I think this is just nonsense. Okay, misconception number 3. It's a conspiracy. This is the argument from fine-tuning. It's kind of similar to the first argument. The claim here is implicitly that one needs a lot of detailed information to obtain a prediction from that theory, which renders the theory non-predictive. Now, the thing is that you just cannot say anything about this without actually looking at a particular model. If you think about what fine-tuning means visually, it means that you have some final state that depends very sensitively on the initial state. But the only way that you can make a statement about it is by having a dynamical law that connects the final state with the initial state. And, in all fairness, no one has any dynamical law for a theory that is super deterministic. So there's just no statement that you can make about it. And why do people even come up with this? Well, they have an intuitive idea that rests on a notion of what states are probable or close to each other. So this argument typically comes in the form, well, if I would only make a teeny tiny change to this initial state, then everything would go badly wrong. But to even make such a statement requires that you have a measure that tells you which states are probable or are close to each other. And again, you just cannot generically make a statement about this without writing down the theory. Okay, so this is an appeal to intuition because it relies on this idea of what it means to make a small change. And so here's the misconception number 4. It would eradicate free will, and there seem to be a lot of people who are bothered by that. Where does this even come from? Well, statistical independence is often referred to as the free choice or the free will assumption in Bell's theorem. That's because it tells you something about, supposedly tells you something about what the experimenter can do with their detector setting. This terminology, I think it's really unfortunate because it raises the impression that superdeterminism puts some really outrageous constraint on human consciousness. I think this really makes no sense because, well, for one thing, choosing a detector setting does not necessarily require any human to do anything. So there doesn't have to be any free will in this free will assumption. But maybe more importantly, free will is hard to make sense of in any theory that is deterministic. It has nothing to do with superdeterminism in particular. I would say if you have a theory in which the future is determined, then free will is a notion that you should give up on. It just doesn't make any sense to talk about it. Now, of course, there are a lot of philosophers who would disagree with that. And the way that they like to argue is that there is a certain way that you can define a notion of free will, which you can do even though the theory is deterministic. And that's all fine with me, really. You can debate this with the philosophers if you want. The point I have here is that this whole debate does not depend on whether the theory is deterministic or super deterministic. It also doesn't make a lot of sense to me to obsess about this relation between the detector setting and the hidden variables, because the laws of nature always constrain what we can do. And again, that's not specific to superdeterminism. An example that I like to mention is that if you have two fermions, you can't put them into the same state. We all know that, but no one goes about and says, oh, well, that puts a constraint on the free will of the experimenter because they're not able to put these two fermions into the same state. This would just be ridiculous. That's just the way how nature is. And it's the same with superdeterminism. It may just be the way that nature is. Okay, so this is a red herring. It really has nothing to do with superdeterminism in particular. Okay, so what do we actually learn from all these Bell type tests that have been done? We learn from this that Bell's inequality is violated, and we learn from this that at least one of the assumptions of the theorem cannot be realized in nature, but these tests cannot tell us which one it is. And so by assumption, the superdeterministic theories give rise to exactly the same violation of Bell's inequality. Doing Bell type tests over and over again just will not teach us anything about superdeterminism. This was basically my motivation for why one should think about superdeterminism. Now this was a lot of words. Now I want to show you at least 2 equations or something. There are a few toy models for superdeterminism, for which you find references in the paper that I mentioned in the beginning. There are basically only 3 theories. The probably best known is 'Two's, which you will hear about tomorrow, I guess. Then there is Tim's, which you will hear about in a moment. And then there's my little approach that I briefly want to flesh in the final slides. So, you know, I have a background in particle physics, so I like to conceptually think in the terms of particle physics. And the way that I like to think about this superdetermined evolution is by way of a path integral. So normally, if you use the path integral in quantum field theory, you say that the system takes all possible paths, and you get a probability distribution over the outcomes. So the modification that I'm proposing, and I'm working on this with my student whose name is Sandra Donati, is that the system in the end takes only one particular path, and that's the path for which the end state optimizes a particular functional. And the question then comes down to, well, exactly what is the functional that the path is supposed to optimize? And we know that to solve the measurement problem, you basically need something that gives you a large contribution for states that are in a quantifiable sense very classical. So, and here is the path integral that we're currently looking at. You know, in the end, maybe that's not exactly what will work, but that's what we are looking at today. It uses the same formalism that we have in quantum theory. So we have some wave function that is an element of the Hilbert space, and we could make this a Fock space, but for now we just have a Hilbert space. I think the complication is not going to the Fock space. And then in the path integral, we sum over all paths in configuration space. Okay, so we do not sum over classical paths. We sum over all the paths in configuration space that are encoded in these factors in the expansion of the wave function. And then where we have an exponential of some function that basically plays the role of what is usually the action. And so that's the question, exactly what goes there. This function that we are trying now here, it has 2 factors. The first one, you can see this just by looking at it. It will be stationary if the wave function fulfills the Schrödinger equation, and one can actually formally show this. And then we have a second factor that, roughly speaking, measures the quantumness of the state. And the higher the quantumness, the more this path will be suppressed. So why do I write something funny like quantumness and not actually an equation? It's not that I don't have an equation, it's that I have too many equations. What could go there is basically any measure that you can find of entanglement, or whatever is the opposite of classicality. And there are literally dozens of them that people are talking about in the literature. So we are right now basically looking which one works best. I think in the end, it will not make a big difference. So what this term basically does is it will quantify how fast the collapse happens and how it depends on the number of constituents of the system. But qualitatively, I think it will not make a difference exactly what one puts there. Yeah, so how could one test this? Well, all superdeterministic theories have some things in common, which is notably that they are deterministic in contrast to quantum mechanics. And this means if you have exactly identical measurement setups, you will get identical measurement outcomes, in contrast to what you would get in quantum mechanics. Of course, the question is, how do you actually know that you have an identical measurement setup? Again, this is something which, strictly speaking, you can only show by looking at a theory. But I think there are some generic statements that can be said about this, which is that most of the variation you will see in the measurement outcome probably comes from the degrees of freedom of the detector itself. So if you can limit the number of degrees of freedom of the detector, or you can freeze them in to as good as you can. Of course, you can't entirely freeze them in, because then you can't detect anything with the detector. But you want to limit them as good as you can, and then you want to measure in a sequence as quickly as possible. Then you should see an autocorrelation in the time series of the measurement outcome that, according to quantum mechanics, should not be there. And this generally requires small code systems in which measurement can be repeated in rapid sequence. I think that we would learn much, much more from experiments of this type than doing Bell-type experiments over and over again. Okay, so this brings me to my last slide. I do not want to repeat everything that I just told you. I just want to repeat the major point that I want to get across, which is that superdeterministic theories are not interpretations of quantum mechanics. They are more fundamental theories from which quantum mechanics derives. Okay, so that brings me to the end of my talk. What do I do now?
Okay, thank you, Sabine. No, please leave the slides on for now. Okay. There is time for questions. So for the audience, does anybody have questions? You can just speak up if you do.
Hello, you are talking about, it's Marian. I couldn't put my video. It's Marian Kupczynski. At the beginning, you told that probability is the probability of the particle. Probability is a property of the random experiment. So you dismiss. You are saying that quantum mechanics. You talk only on this individual interpretation of quantum mechanics, but usually in every domain of particle physics, and we are mostly using statistical interpretation of quantum mechanics, and quantum mechanics predicts some regularities in quantum phenomena and things like this. You are talking about that you can reproduce each time. If you have the same preparation, you should give the same outcome. So you neglect completely that you have measuring devices, different PBS and detectors, which you cannot control internal parameters. So initial preparation has nothing to do that you will obtain the same result. And if you have statistical interpretation, the collapse is nothing magical, nothing instantaneous. So why you just you don't need superdeterminism. Moreover, you taught in Berlin, you have the statistical independence, and it should not be statistical independence, because in each settings you have different parameters describing measuring devices, and it was shown that you can explain in locally causal way correlations in real experiments, and so you completely dismiss this type of research. Besides, if you are talking about particle physics, I cannot see how from your Schrödinger path integrals you will reproduce standard model and all these things. Thank you.
Okay, this was like 5 different questions. As you came to the end, I had already forgotten the first one, but I'll try to do my best. Okay. So as to the statement that probabilities really only make sense if you're talking about an ensemble, I entirely agree with that. Nevertheless, we want a theory that actually describes what the single particle does. And if your point was to say that quantum mechanics is not the right theory for that, then I entirely agree with this. Now about the point that you know, the measurement apparatus changes from one measurement to the next, that's exactly the problem. This is why I say you have to limit the degrees of freedom. You have to try to freeze them in to the extent possible. You can ask, how do you know that you actually prepare the state the same way? This depends, of course, on what you think the hidden variables are. As I said, strictly speaking, you can only make a statement about this if you actually have a model. But what you can do in any case is that you can make repeated measurements on the same state. So this reduces the number of degrees of freedom further. Of course, you will never get entirely rid of the variation that comes in from the measurement apparatus. So the question is, can you reduce this variation to a level so that you can actually measure the autocorrelation time? You seem to be referring to a certain type of theory or interpretation that I am not familiar with, and so cannot say anything about it. For what the standard model is concerned, so the reason that I was trying to write this down as a path integral is that I think it has an obvious way to be generalized to a quantum field theory. And I haven't thought about it all that much, because for now it would be fine if we could make it work with quantum mechanics. But this thing is Lorentz invariant, and I think you can second quantize it, and a priori I don't see the problem with that. And so in the end, you should be able to get back the standard model, I think.
Okay, so more questions. Please try to keep them focused. So.
I have a question, if I may.
Yep.
You hear me? Yes. Tomorrow I will talk about roughly the same subject, except I'll put in much more equations. And from the equations, then you will see that what I consider superdeterministic theories are a small subset of all quantum theories. So most quantum field theories do not do not allow you to simplify them into something super deterministic. But a very special subset does. It only differs from the quantum theories we are using today at very high energies, where we have no experimental data at all. So what's wrong about assuming that at very high energies something very special happens? If so, these theories would be highly predictive and non-trivial, because they tell you something about the domain of physics to which we have no access today, but perhaps tomorrow. So a question to you then in the very end is, what you call a super deterministic theory, is that a subset of all quantum theories, or is it totally different? Because the latter, I think, is not necessary. And well, maybe you can first try to answer that question.
Well, I would just say they're not quantum theories. It's like they're neither classical, not quantum. But maybe let me try to answer the question in a little different way. I think, if I understood this correctly, you were making a statement about the possible interactions that you can have in the theory.
Yes.
Yes, and so this is something that we just have not thought about. It may possibly be, but since we're only dealing with quantum mechanics, and we have not even written down exactly what the Hamiltonian looks like, I just don't know. It may very well be that there are only certain types of interactions that you can write down. Yeah, so
but you very well know that.
Forward to your talk.
You very well know that only very little is actually known and understood today. We have the so-called standard model of the subatomic particles, but much of the standard model is unknown. And in fact, everything that happens at very high energies is unknown. So it's obvious that if you make a change in the theory at very high energies, nobody will notice any difference except in the area of determinism, a lot changes. If you change the very high energy behavior of your particles, you will change all the statistical consequences of particle theories. Although whenever you do a scattering experiment, you see the same statistics, but you don't see the same actual events. They will depend a lot on what happens at extremely high energies. So there's an enormous amount of space there to modify your theory. And I claim that if you modify our theories in a very, very special way, which has no effect on the low energy behavior, so it will just be the standard model again at low energies, but at very high energies, it will be something else. And this would make these theories very predictive and, to my mind, also very important.
Yeah, I vaguely feel like we've had this discussion before.
Yes.
I think the difference is that I implicitly assume that effective field theory remains valid. So you can basically forget about all the high energy degrees of freedom. And that may just be wrong. But yeah, this implicitly goes into what we are trying to do.
So I saw that you wrote only one equation, which I thought was a very vague equation. What I'm trying to do is try to write down accurate equations that define for you what a superdeterministic theory is, and what the quantum theory is, and how one can be a subset of the other. This is not obvious at all, but it turns out to work that way. For instance, the question you asked about what makes quantum theory produce random results. And the answer is, in a superdeterministic theory, random out equals random in. You don't know the initial state, so don't be surprised not to be able to predict the final state. What's strange about that? That's totally reasonable in any scientific theory. If you don't know exactly what you're doing, you'll have error bars around your results about the prediction. Nobody should be surprised about that.
Yes, I entirely agree with that. So for me, the mystery is not so much where does the randomness come from, but why do you always end up in a detector eigenstate? And
well, that's the collapse of the wave function, and that is exactly where also a superdeterministic theory says, well, if you have a true description of the actual initial state, your description of the final state will also be true, will be accurate. But of course, we don't know what the initial state is, so don't be surprised that we don't know what the final state is. And don't be surprised that when you measure something, you have some extra information that you didn't have before, so you prefer to look at another wave function, which happens to be the collapsed one. That's just an improvement of our understanding, just like it is in any non-quantum statistical theory, like the van der Waals gases. Of course, when you observe an atom in a van der Waals gas, as soon as you observe it, you know for sure the probability distribution has that particle cause a delta peak in your probabilities. That's not a collapse of a probability function. It is just a different description of what we know today. So that's a psi-epistemic story, which does where such psi's never need to be collapsed manually. Nature will do it for you.
Yes, as I said in the beginning, you can have the certitude that the wave function only gives you some probabilistic, some makes only a statement about the information that you have about the system.
Yes.
But then you are implicitly giving up on reductionism, as I said in the very beginning.
Why?
Well, because then this theory is not the theory for the constituents of the system. You know, you somehow have to, either you don't have a theory for the constituents of the system, or they're actually incompatible with each other. You somehow have to.
Well, maybe you can continue discussion tomorrow if you will be listening. Then I'll try to explain how it goes. And we are just doing ordinary science, you know, working with the uncertainties that modern science is coping with. Of course, we don't know everything. Nobody should be surprised about that. Nobody should complain about that. That's the way our field works. We have limited information about the true state we are in. So limited information going in equals limited information getting out. So that's not something specific for quantum theory at all. Any deterministic theory underlying it will have the same property.
That's
Okay,
right.
I would suggest to pass to the next speaker, and then since we have many questions in the chat and people raised hands, in case at the end we postpone these questions and we try to address them at the end. So I would thank Sabine for now and pass to the next speaker. So Sabine, please remove your sharing, and team, please prepare your slides. So perfect. So
Okay.
next, yep, it works. So next speaker is
And
Tim Palmer. So please.
Can you hear me?
Yep.
Okay, great. Okay, so what I want to do is give a specific example of what Sabine calls a super deterministic model, and it's something I call the invariant set model of quantum physics. I won't say very much about myself. If I have a little bit of time at the end, I'll say a little bit about myself, but basically I'm in Oxford in the physics department. Sorry, I need to, dear, sorry, just 1 second. Yeah, the talk is based on a couple of papers. One appeared in the Proceedings of the Royal Society about a month or so, a couple of months ago. Paper called Discretization of the Bloch Sphere, Fractal Invariant Sets and Bell's Theorem. And I'm happy to send people either preprints or the link to the paper. The other is from an essay written for the Foundational Questions Institute, which is a bit less technical, but goes into some of the issues about undecidability and uncomputability, which I think is a relevant issue here. I don't want to repeat what Sabine said, but I just want to again stress that what we're not talking here about is an interpretation of quantum mechanics, but an approach to quantum physics that somehow goes beyond quantum mechanics. And like Sabine, I feel very strongly that there's no compelling reason to believe that quantum mechanics is a fundamental theory of physics. Sabine mentioned the close similarity between the Schrödinger equation in the density matrix form and the Liouville equations. And you know, the Liouville equation for a chaotic system is linear, not because the chaotic system is linear, but that the linearity expresses conservation of probability. So my own view is that because of that close similarity, the linearity and indeterminism of quantum mechanics is unlikely to be a fundamental feature of quantum physics itself. There's something quite interesting, which I'm not going to dwell on, but I think is something people might want to think about, which is that the continuum seems to play a much more fundamental role in quantum mechanics than it does in classical mechanics. In classical mechanics, we can very simply discretize systems which are based on the continuum. And a good example is, you know, to do weather forecasting from the Navier-Stokes equations. We can very easily discretize the Navier-Stokes equations and produce, you know, pretty reasonably good forecasts of the weather. But the continuum seems to play a much more fundamental role in quantum physics through the complex Hilbert space. And if you try to discretize that, you violate one of the axioms that Lucien Hardy formulated a few years ago as what he calls reasonable axioms for quantum mechanics. The continuity axiom that you can get from one part of Hilbert space to another by a continuous transformation will violate that. And so you will not approximate quantum theory. So that's, I think, quite a deep concept that we need to think about when we try to formulate more finite-based, discretized theories of quantum physics. The property, as again Sabine said, property of non-locality makes unification with GR very problematic, and my own view is it's perhaps the single most important barrier to the prevention of us formulating a quantum theory of gravity based on quantum field theory and GR. And I want to show in this theory that by going towards the thought of a more finite theory of quantum physics, we can actually evade this conclusion that physics is not locally causal. So I'm going to start off in a place which seems extremely different from quantum mechanics, and in fact has been very much motivated by nonlinear dynamical systems theory, which is to think of the universe as a nonlinear dynamical system, but one that evolves precisely on a particular geometry of chaotic systems, a fractal invariant set geometry. And the basic notion then is that the laws of physics, a little bit not totally dissimilar to general relativity theory, but now thinking about state space rather than space-time, that the laws of physics at the most primitive derive from the geometry of this invariant set. So I want to just kind of focus on that a bit more, because I'm not talking, the example in that last figure was from the Lorentz attractor, and that's not exactly the fractal attractor I want to discuss. So what I'm imagining here on that curly line to the left of the diagram is a state space trajectory. And the idea is that if you zoom into it sufficiently with sufficient resolution, you will actually see that it comprises a helix of trajectories. And the number I'm going to denote by 2 to the power m. And if you zoomed into one of those helix of trajectories, you would see that too was comprising a helix of 2 to the power m trajectories. So if you take a cross section through that, if you continue that process and take a cross section through one of those tubes, the cross section is on the bottom middle there, you'll see something that as you take more and more of these fractal iterations looks like a set of disks within disks within disks. And those of you who might know the mathematics will know that this is a kind of topological representation of a number system, which is incredibly powerful in pure mathematics, used routinely in number theory and so on, called the p-adic integers. So it's the set of so-called p-adic integers would be homeomorphic to one of these fractal disks. Here, the p is 2 to the power of m. And we'll come back to that in a little bit later in the talk. The other thing I wanted to say was the notion of measurement, if you like, or decoherence. Sabine mentioned the many worlds theory, where somehow trajectories branch into separate branches. Here at the coarsest fractal iterate, you might think of these trajectories branching. But in fact, if you zoom in and think about these helixes of trajectories that go round, then in fact, these are just exponentially diverging from each other in a way very similar to classical chaotic instability. So there's no branching at a high enough fractal iterate. And the branching is presumed to sort of go in the way of, or the divergence of trajectories are presumed to lie into discrete clusters. And here I've just shown 2 clusters, which I call A and not A. And these are presumed to correspond to measurement eigenstates or the observed measurement outcomes. And it means that we can label symbolically each of the trajectories in one of these fractal helixes with a symbolic label, A or not A, according to whether that trajectory evolves to the cluster A or the nonlinear cluster not A. Okay. Now, the purpose of this paper, the Procroy-Sock paper, is to show that you can use the language of complex Hilbert vectors and associated tensor products, for that matter, to describe probabilistically this notion of a helix of trajectories. Now, I'm not going to have time to explain why, and I would just refer people to the paper for the details. But the idea is the following, that you have 2 parameters, theta and phi, of a complex Hilbert, a sort of qubit vector, qubit state. The theta parameter is in the amplitude, as you can see there, and it's such that the cosine squared of theta over 2 gives you the frequency, the number of the trajectories in the helix that evolve to the A cluster. And sine squared theta over 2 gives you the frequency of members in the helix that evolve to the not A cluster, the other cluster. Now, a crucial point here is that the number of trajectories in the helix is finite. So this cosine squared theta over 2 is a rational number. And moreover, it's a number which has a finite binary expansion. And this means that the cosine itself is a rational number. Now, the complex phase phi denotes essentially a rotation around that helix. And again, because there are a finite number of trajectories around the helix, phi itself can only be a rational multiple of pi, or 2 pi. So where we differ from quantum mechanics is that these Hilbert vectors are only defined where the squared amplitudes and the phases are rational numbers. This is quite a crucially important restriction over standard quantum theory. And essentially the irrational, for example, the irrational values of phi would correspond to angles which lie in the gaps, in these fractal gaps in the helix that I talked about, the gap between the trajectories. Okay. I'll explain this. You'll see shortly why this is a superdeterministic theory, but I'll just go through a couple of more sort of semi-technical slides for the moment. Now, everything in the theory rests on a crucial theorem in number theory called Niven's theorem, which basically says if you have an angle between 0 and pi over 2, and it's a rational multiple of pi, and in particular, it has a finite binary expansion, then necessarily the cosine of that angle will be an irrational number. So as you know, for example, if phi was pi over 4, then its cosine is 1 over the square root of 2, which is irrational. And that's a generic property of this cosine function. And I've just shown in the diagram, I've shown values of phi every, expressed in terms of, rational multiples of pi, and the cosine. And you see in general, the cosines of the dashed lines, they don't line up in any way with the solid lines. And that's a generic property of Niven's theorem. So a particular example of this is if you took two Hilbert vectors. One has the angle phi in its amplitude, and the second has its angle phi as a phase angle. Then in quantum mechanics, these two are related by a unitary Hadamard type transformation. So Hadamard would take you from the first psi1 state vector to the second psi2 state vector, and they would be both well-defined states or points on the Bloch sphere. However, in the proposed discretization, and by using this Niven theorem, then if psi1 is defined in this discretized approach, which means that the cosine squared of phi over 2 is rational, then necessarily psi2 is undefined, because then the phi angle cannot be a rational multiple of pi. Now this holds no matter how big this discretization is, no matter how big M is. And that incidentally raises a question which I think Gerard asked of Sabine, which is the relation to quantum theory. In these types of theories, quantum theory arises as a singular limit. The continuum of quantum theory only arises when you literally go to... somebody's just turned on a microphone, which is giving it some feedback. If you could mute, I think it would be good. So, so M equals so you rise at the continuum Hilbert space at M equals infinity, but any finite value of M will not give you Hilbert space. So this class of theories, quantum mechanics, arises as a singular limit, and not in any sense is it contained within these theories. Now I want to say, what does this mean in practice, this type of discretization result? Well, imagine you have imagine you're doing a Mach-Zehnder experiment, and on Monday, you send particles through the full interferometer, and you measure the statistics of the detector outcomes. Now, according to this theory, when you're doing these experiments, and you can describe the state of any of the particles by this standard Hilbert vector, then the phase angle difference, or the phase path length difference between the two arms of the interferometer phi is such that the cosine squared phi over 2 is rational. Now on Tuesday, suppose you do an experiment with the same interferometer, but you take out the second half silvered mirror. So then you're basically asking which way do the particles go around the interferometer. According to the theory, the Hilbert state would be one where the phase angle now arises as in the complex phase. And again, it's this Hadamard which connects the two. Now, what does this number theoretic property imply? It implies that if you ask a counterfactual question, so you say, what would I have observed had I performed Tuesday's experiment on Monday's ensemble? So Tuesday's experiment requires that phi is a rational multiple of pi, but Monday's experiment, it's the cosine of phi that is the rational number, not the angle itself. So in this number theoretic program, it means that these types of counterfactual experiments, what would I have observed had I performed the which way experiment, when in reality I did the interferometric experiment, is undefined. And that's really, the sort of thing that Bohr, of course, through his principle of complementarity, focused on in many of the discussions in the early 20th century, and is a kind of one of the defining features of quantum mechanics, and essentially underpins the non-commutativity of quantum observables. The fact you cannot simultaneously perform, say, a position and a momentum measurement. That basically means that if in reality you did a position measurement on a particle, and then you ask the question, what would I have observed on that same particle had I performed a momentum measurement? Quantum mechanics tells you that's not possible, and this number theory gives you in a sense, a reason or a theory why that has a reason. And the reason is, in the counterfactual experiment, you're actually perturbing the state of the real world into one of these fractal gaps in the invariant set. So exactly the same arguments apply to Bell's theorem, and I'm not going to go through this in any detail, except to say that, so you imagine you're doing a Bell experiment, you have a particle pair represented by hidden variable lambda, some specific value. And let's say in reality, Alice measures her particle with her detector set in the 0 position. This is a standard Bell type experiment where you have each Alice and Bob can choose between a 0 orientation or a 1 orientation of their apparatus. So we assume in reality that in a particular experiment, particular situation with a particular particle labeled by lambda, that Alice does and Bob both do the 0 orientation experiment. So that has a non-zero probability. Now, according to this invariant set model, and again, I'm not going to say why, but it's basically for the same number theoretic reasons. It's to do with this, the rationality of phi and cosine of phi. Then it turns out that the probability that the experiment 1-1 was performed, that's a counterfactual, has got the same probability according to this theory. But the probability that the 0-1 experiment or the 1-0 experiment was performed, given that the 0-0 experiment was performed, those are both identically 0. The 0-1 and the 1-0 experiment lie off the invariant set in this fractal gap. So as counterfactual experiments, they become non-ontic, if you like. They are impossible. They're not parts of the theory. Now, this is precisely the violation of statistical independence that Sabine talked about. But this violation of statistical independence comes about when you consider these counterfactual alternative experiments that might have happened but didn't. And in this particular theory, these counterfactual experiments, if they don't lie on this fractal invariant set, if they correspond to states in the gap, then they're not consistent with the theory. I just want to make two very quick points on this point without carrying on. One is to do with fine tuning. I mentioned that p-adic numbers are a very natural way to represent fractals. And for those of you who know these things, there is an associated metric associated with the p-adics called the p-adic metric, not unsurprisingly. And it turns out that points which don't lie on the fractal are p-adically distant. The distance is at least p, and if p is a large number, 2 to the m large number, then they're distant from the points which lie on the fractal set. So this is my refutation of the fine-tuning argument, that fine-tuning depends on a choice of metric, and the natural metric to use with these fractals is the p-adic and not the Euclidean metric. The second point very quickly is that, which is about this notion of predictability. These fractals are actually technically non-computable, which is what the theory, what the essay I wrote about for foundational questions. So in a way, you certainly can't decide by algorithm ahead of time whether a particular setting of Alice and Bob for a given lambda will lie on the invariant set or not. So, you may as well, I think this is what Gerard was saying, you may as well, for all practical purposes, treat the outcomes as random. But ultimately, this is underpinned by a deterministic theory. Okay. So because this theory is based on Hilbert vectors, albeit ones with these rational amplitudes and rational phases, the theory violates the Bell inequality exactly as does quantum theory. But because it violates statistical independence, because of this, essentially these counterfactual states have zero probability when they don't lie on the invariant set, then really this gives rise to a rather novel, I think, way to interpret Bell's theorem and the violation of Bell inequalities without giving up on local causality. In other words, without giving up on the basic principle that underpins relativity theory. Okay, I've sort of finished my talk. I'm going to do something which Sabine will hate me for, but which is to give a couple of quotes. But this is perhaps useful for two reasons. Well, two reasons. Maybe one is to just give the quote, but also my own background is I did a PhD many years ago in Oxford under the cosmologist Dennis Sharma. But during that time was very strongly influenced by Roger Penrose. And Roger was in fact my internal PhD examiner. And I always, have taken inspiration from some of his critiques of quantum theory. And one that I very strongly agree with was a statement he made some years ago that to understand quantum non-locality, we shall require a radically new theory, not just a slight modification of quantum mechanics, but something as different from standard quantum mechanics as general relativity is from Newtonian gravity. It would have to be something which has a completely different conceptual framework. And that's totally motivated my work and this invariant set type of model. And then the second, the second quote, Dennis Sharma, my supervisor, was actually himself supervised by Paul Dirac. So I have some sort of distant affiliation there too. So I'm always pleased to remind people that Dirac was himself a critic of quantum mechanics, despite, of course, being one of its seminal founding fathers. And this is a quote from the Linchaean Academy a talk he gave in the 70s. One can always hope that there will be future developments which will lead to a drastically different theory, I've emphasized, from the present quantum mechanical theory, and for which there may be a partial return of determinism. I like to think of this idea of sort of non-computable determinism as being perhaps qualifying for that type of notion that he was talking about. So that's my talk. Thank you very much.
Thank you, Tim. Very nice talk. So questions. It's time for questions. So please speak up if you have one.
Hi, I have a general question that since these theories like black hole physics and general relativity, they are better on a better footing. So is there any instance where the new theories like super deterministic theories and your work have been tested on results from black hole physics or general relativity?
Well, I speak for myself. I let Sabine may say something. I mean, I think the great area for the future is testing quantum mechanics under condition, on systems whose self-gravitation is not negligible. And, we don't yet have the ability to do that in the laboratory. And the question about whether things like superposition and even entanglement will still hold for such self-gravitating systems, I think will be a major step forward in our experimental capability. My own view from this model, the suggestion is that, well, I don't believe superposition is in a sense a fundamental property of systems, and the more the self-gravitation of the system, the less the manifestation you will see of these properties of superposition or indeed entanglement. So I'd make that as a prediction of my particular approach. I don't know what Gerard says about that sort of thing, but this is an exciting time, I think, when we can start to test in the lab the quantum mechanical properties of self-gravitating systems.
Right, thanks.
May I say something? With that, you're assuming that gravity somehow is an exceptionally different kind of force than all the others. But on the other hand, gravity, like any other force, is an action principle. So one can also say that since we have a theory based on action and reaction, gravity is very similar to the other forces. But I have a more relevant question, and that is when you talk about the continuum, you say the continuum is an essential feature of quantum mechanics. However, we can imagine living in a finite universe where everything is finite, including the total number of states you can be in. And in fact, when it's common practice in many branches of my field for people to write models where total Hilbert space is just replaced by a finite vector space. And that you do if you realize that your calculations can never be infinitely precise. For example, we have the well-known number alpha defines such a constant, 1 over 137 and something. It is not known whether that number should be a real number or a rational number. Both possibilities are still open, and we will never be able to figure out which is true by any measurement, as far as I can imagine. But so why do you think that the distinction between continuous and discrete is so essential? I would contradict that. I think there's a natural overlap between the continuous theories and the discrete theories.
Okay, just to come back to the first point. Of course, I mean, general relativity is not a theory of a force; it's a theory of gravity. And of course, I think the form of the action in general relativity is in a way quite different from the form of the action, say, in electromagnetism, which is why the sort of standard spin 2 versions of quantum of electromagnetism just don't describe gravity. So there's something different about the form of gravity, the form of the action, that makes it quite distinct from other types of gauge theories, for example. And my own view is that that's a reflection of the fact that gravity is a theory of geometry, and well, in a sense, this is what I'm trying to bring to the discussion about quantum mechanics, but albeit fractal geometry. As far as the continuum is concerned, I mean, I'm talking about I'm not talking about the fact that you can't have a finite system comprising a finite number of particles. But the state space in quantum mechanics is the continuum Hilbert space. So in other words, you use the field of complex numbers to describe your state space. And the question is, can you, in some sense, start to discretize that complex field, even when you have a finite number of particles? And Hardy, Lucien, I mean, I'm referring really to Lucien Hardy's work, where he ends up concluding that the continuity axiom, the ability to have unitary transformations, but continuous unitary transformations between any 2 states in this complex Hilbert space, even if it's a finite dimensional Hilbert space, is an essential aspect of quantum theory. And if you start to violate that, then then your theory is no longer quantum theory.
So there I agree. So the question is really the dimensionality of Hilbert space, whether it's important that is infinite, or can you very well make models of nature where dimensionality of Hilbert space is finite. I agree that when you superimpose states, you can choose any superposition coefficients, real or rational, whatever you like.
Yeah, but that's the question. You know, the complex number, the field of complex numbers seems to play a more fundamental role in quantum theory than, say, the field of real numbers does in classical theory. You know, you can easily discretize state space in classical theory, and you don't really introduce any fundamental obstacles, I don't think. But in
you can introduce probabilities, which are also, of course, continuous in classical physics.
Yeah, but anyway, I mean that's what I was talking about. Is how do you go about, if you like, discretizing the continuum of Hilbert space, not the continuum of space-time. I mean that's another issue.
Okay, thanks.
Okay, I do have a question actually. So, if understood correctly, basically you mentioned that time evolution makes you pass from a dense set, like rational numbers ones, to a different dense set, and this is at the basis of complementarity, like for instance Bell inequality and so on. Now, my question, I'm not familiar with the details of the theorem, but my question is that, is there any sort of recurrence time where you go back to the same set, or at least you overlap with the same set, and can this give observable consequences in principle?
Well, I think if you have a theory which is ultimately based on finite numbers, then there will be a natural recurrence time. But that may be, of course, extremely long and extremely large. So I don't know in practice whether that has any sort of experimental consequence. What I'm saying, by the way, is not that you sort of go from one set of numbers to another set of numbers. It's that you have these two. I mean, if you like, the angles where the cosine is rational is kind of a discrete set from the set of angles which are themselves rational multiples of pi. And so if your states are described by one of those number systems, and then you ask a question which is inevitably a kind of counterfactual question, which would, for it to be well defined, you'd have to invoke one of the numbers from the other set. Then because they're disjoint sets, then you know that state cannot exist.
Okay, thanks. So, more questions?
People can ask Sabine a question as well, of course.
Okay, I have a question. In principle, you are talking, as I believe, also in local causality, but it doesn't mean why you are talking about superdeterminism, because you can have local causality without talking superdeterminism. In principle, your rho, you are saying it's probability. But if you're writing rho 0, 1 in your example, in some sense you describe some ensemble, so you get P0. So there is no superdeterminism in this respect. If you the problem is superdeterminism related with Bell considerations that something is influences experimental choices of the settings, but you can have violation of the statistical independence if lambda depends on the settings. And this is natural that lambda can depend on the settings because instruments are a big chunk of equipment which are governed by their own parameters. So it can be really explained that it's you don't need superdeterminism to have setting dependence of the lambdas, and in this case, violation of Bell inequalities.
Well, look, formally, I mean, Bell's theorem you can formulate as a theorem in mathematics. So, under certain situations, the theory must satisfy or must violate Bell inequalities. Now, the usual, I mean, you know, the usual argument is that, you know, if you imagine these particles, ensembles of particles being created, you know, hundreds or thousands of years or millions of years, whatever you want, before you ever measured them, you know, then whatever their properties are, this would be the standard theory. It's not the one that I endorse, by the way. The standard argument is that the hidden variables, you know, the properties or probabilities of the hidden variables shouldn't depend on, you know, the details of what happens in the long distant future. So the, you know, the standard argument is if you want to invoke some relationship between the statistics of the hidden variables and the measurement settings, then you're introducing something somehow conspiratorial into the mix, and people typically don't accept that.
No, this is a false argument, because in this
I know
case,
it's a false argument. I agree it's a false argument, but I'm just trying to tell you why people think this.
This is false argument, of course, because you know, okay, so I can probably you don't know my paper anyway, so but I can send. Usually, the problem is that the source is producing some coordinated signals, and they arrive to detectors, and in function of the setting of detectors, there is no predetermination. The thing which is broke conclusion of Bell is that there is no predetermined outcomes, because the outcomes are not predetermined because the parameters of the detectors in different settings are different and they are not controlled. Thank you. But I like your lecture, yeah.
Well, I think we agree in a sense, because if you relate the hidden variables to the detector settings, then you have some kind of a super deterministic theory. I guess we're all agreeing that, you know, this has been a neglected area in the analysis of the Bell theorem. And my view is that it's actually, you know, it's the reason why we haven't been able to move on beyond quantum theory, because things like pilot waves just don't really help. You just end up with something much more explicitly non-local, which is very unattractive to people. So that's why people have just stuck with quantum mechanics, because the alternatives seem even worse. But now I think we're on the cusp, you know, with Gerard and yourself and Sabine and myself and others, we're on the cusp, I think, of some quite radically new thinking where these ideas are exposed to being quite false.
Okay, thank you, Tim. I would just select a couple of questions from the chat, and they can be for either speaker, so please feel free to intervene, either of you. So, for instance, Albert was asking to Sabine about, either of you can answer, how do I get the Born rule from superdeterminism? So it's about the Born rule.
Who wants to answer that? I mean, my view, I'll just tell you in a nutshell, my view is once you use vectors to describe probabilities, in other words, you know, you have an amplitude times one direction plus an amplitude times the second direction, then Born's rule is a consequence of the Pythagoras theorem. There's nothing mysterious about the Born rule. So I use Hilbert vectors to describe the ensemble statistics of my invariant set. And so because I use vectors, then necessarily the Born rule follows. The Born rule being that the squared amplitude gives a probability. If you do that, if you violate the Born rule, then you're violating Pythagoras' theorem. So I see no possibility, but that the Born rule must be satisfied.
Thank you. Sabine, do you want to add something?
Yeah, so I think there are two parts to Born's rule. One is the particular way that you calculate the probabilities by taking the square of the amplitude. The other one is the question, how do you get the prefactors to match those that you have in ordinary quantum mechanics? So I think Tim basically answered the first part. It's like the moment you have your theory with vectors in the Hilbert space, Born's rule is what you get. And formally, that's basically what Hardy's proof tells you. Like this is the only probabilistic calculus you can put on a theory of that type. So this leaves the question, like, where do you get the prefactors, like the weights of the different components in your expansion to match those of quantum mechanics? And again, I can only say that you have to find the right dynamics of your theory. Basically, I think what it will come down to is that your theory needs to have a mix of some kind of attractor mechanism that brings your state into a detector eigenstate. And then on top of this, you need some kind of randomness that is probably strongly chaotic, which reproduces a distribution that has to match that of quantum mechanics. And so I know that this is vague, I wish I had an equation to fill in the blanks, but that's the best I can do.
Okay, thank you, Sabine. A last question from the chat. Well, I try to interpret a few of them. Again, for both speakers, is superdeterministic time reversible, or is it not clear yet, or not? So, please.
It is time reversible. In principle, in practice, it's as not reversible as you have it in statistical mechanics. Like if you wanted to reverse it in time, you would have to know very, very exactly what state you are in. So it's basically the same thing. Okay. So it's actually an interesting question. Maybe I should have said something about this, but forgot about it. Of course, the collapse of the wave function is, strictly speaking, not reversible in time, because you have a lot of initial states that end up being the same outcome. So in superdeterminism, you never, strictly speaking, do this collapse to one detector eigenstate. It's just that you focus your trajectories in these clusters until you can no longer distinguish them. But strictly speaking, they never fall on exactly the same trajectory.
Okay, Tim, do you want to add something?
I think there must be some element of irreversibility in the theory as a whole. I mean, in my particular theory or model, where I'm using these fractal sets in state space, these arise from, in classical physics, in classical chaotic physics, these arise from systems which have some degree of irreversibility, in that you have some dissipation or something like that, which means that volumes in state space get shrunk to zero volume. The measure on the fractal invariant set in the Euclidean space in which it's embedded is zero. But the question is, where does this irreversibility actually kind of manifest itself? And it turns out that you actually only need irreversibility in very, very small parts of state space to generate this fractal structure everywhere. So, for example, it could be that, at the moment of the Big Bang, or in, space-time singularities or something like that, these are the times and places where some measure of irreversibility occurs. And that leaves an imprint on the whole, fractal structure of the system. So, for all practical purposes, we can use Hamiltonian dynamics in laboratory situations quite well and get away with it. But the theory has to have some irreversibility, I think, at some level, at some place. But that's a detail which I don't have complete understanding of yet.
Okay, thank you. Are there, Gerard, maybe you wanted to say something?
Yeah, I think this is the one place where deterministic theories can be more general than quantum mechanics. Because, of course, in the classical system, you may or may not introduce equations of motion which are reversible. But it could also be that two different initial states evolve into getting to one final state. So that from that final state, you never know anymore what the initial state was. This is possible. But you can but more likely you have something like, as an underlying theory, something resembling a van der Waals gas. So all these atoms, each atom individually obeys a time reversible equation, yet the whole lot, since it contains so many atoms, obeys thermodynamics. And you know the laws of thermodynamics are not time reversible. So, so then it's a question on how precisely you want the theory to be. Now, for me, it's very important that if you have an underlying superdeterministic theory, that you use the equation of the theory in principle with infinite accuracy. Like in a discretized theories where you just work with numbers, which are infinitely accurately defined. In that case, the question of time reversibility then suddenly becomes very interesting. It may or may not be time reversible. It may or may not be that two different initial states evolve to their same identical final state. This is possible, but looking at nature, it's more likely that we should be, it should suffice to look at models which are time reversible. So this is my favorite today, but I might change my mind tomorrow about the underlying theory being not time reversible. It's conceivable.
Okay. Okay, so I would close the session now, and I would thank both the speakers for the nice talks and for answering many, many, many questions. Thanks. And I would invite you all to the talk by Professor Toft tomorrow at the same time on similar topics, but different. Okay, so thanks. Bye.
Thank you.